These are the Math 205 Lesson 5 class activities. Write the linear combination as a matrix times a vector. Okay, so my matrix is going to be putting those three vectors into a matrix together. So it's going to be 6, 2, 7, 1, 1, 1, 1, 1, and 1, 2, 3, 4. And then I'm going to multiply by a vector holding the weights. So my weights are 4, -3, and 2. Write out the matrix equation AX equals B. So I have A, which is 1, 1, -3, 3, 5, -7, and -4, 2, 6, times X, which is a vector. I know that because it's written in bold. And then equals B, which is given, -2, 4, 12. Okay, so X is my vector of unknown weights, and I need to know how many to put in that vector. So in order to figure it out, I'm going to say, well, A is 3 by 3, and B is 3 by 1. So in order to be able to multiply a matrix times a vector, the inner dimensions have to match. So this vector has to be 3 by something, so that these two 3's would match. And then the answer is the outer dimension. So my answer has a 1. So my right is my outer dimension. So here's my 3. This has to be a 1 to make this come out to be a 3 by 1. So this has to be 3 by 1. So that means I have 3 entries in here. X1, X2, and X3. Now if I want to translate this to a vector equation, each column of my matrix is a vector, and my X vector is my unknown weights. So I have 1, 1, -3 times X1 plus 3, 5, -7 times X2 plus -4, 2, 6 times X3 equals -2, 4, 12. Translate the matrix equation AX equals B to a system of linear equations. All right, so when you multiply a matrix times a vector, you do the row times the column. So I'm going to have X1 plus 3X2 minus 4X3. So I multiplied each entry in the row times the corresponding entry in the vector, and then I added them up. So it's the dot product of the row and the vector. And because I'm multiplying the first row times the first column, that should give me the first row, first column of the answer vector, so I get -2. Then I'm going to multiply row 2 times my vector, and I should get 4. So I have X1 plus 5X2 plus 2X3 equals 4. And then finally, I'm going to do the third row times the vector, and I should get 12. -3X1 minus 7X2 plus 6X3 equals 12. Okay, now I want to translate this system to an augmented matrix and row reduce it to solve, or state that it's inconsistent. So my augmented matrix is going to be 1, 1, -3, 3, 5, -7, and -4, 2, 6, augmented with B, which is -2, 4, 12. So to row reduce, I want that entry to be a 1, so that's done, and then I need to knock out everything beneath it. So I'm going to make 2 moves at once here. I'm going to replace row 2 with itself plus negative row 1. And I'm going to replace row 3 with itself plus 3 row 1. Okay, so row 1 isn't changing, so I'm going to copy that. 1, 3, negative 4, negative 2. Now row 2 is going to be itself plus negative row 1. So I get 0. 1 minus 1 is 0. 5 minus 3 is 2. 2 minus negative 4 is 6. And 4 minus negative 2 is 6. And then row 3 plus 3 row 1. So negative 3 plus 3 is 0. Negative 7 plus 9 is 2. 6 minus 12 is negative 6. And 12 minus 6 is 6. Okay, so column 1 is set. I'm going to move over to column 2. And I want to first make that entry, that pivot entry, a 1. So I'm going to scale that row by a factor of 1/2. So row 2 is going to become 1/2 row 2. I'm just copying the other 2 rows before I do anything else. Okay, scaling row 2 by 1/2, I get 0, 1, 3, 3. Okay, so now I have a 1 as my pivot position. I'm going to use that 1 to knock out this 2 that's beneath it. So row 3 is going to become row 3 minus 2 row 2. Okay, so row 3 minus 2 row 2. So 0 minus 2 times 0 is still 0. 2 minus 2 times 1 is 0. Negative 6 minus 2 times 3 is negative 12. And 6 minus 2 times 3 is 0. Okay, so I've now done enough row reducing to be able to back substitute and solve for x1, x2, and x3. So my third row here says negative 12 x3 equals 0, which means x3 has to be 0. Put a 0 there. And then my second row says that x2 plus 3x3, which is 0, equals 3. So x2 is 3. And then my first row says x1 plus 3x2, so that's 3 times 3, that's 9, minus 4x3, which is 0, equals negative 2. So that means x1 is negative 11. Now we want to multiply our matrix A times the answer we just got to verify that we get the B that we were given. So my matrix A is 1, 1, negative 3 times, and then 3, 5, negative 7, and negative 4, 2, 6. And I want to multiply by the vector we just got as our solution, x, negative 11, 3, 0. And I should come out to B, which was negative 2, 4, 12. Negative 2, 4, 12 is the B we were given. So let's see, I'm going to multiply first row times the vector. So that's 1 times negative 11, which is negative 11, plus 3 times 3, which is 9, plus negative 4 times 0, which is 0. And then I'm going to do the next row, 152 times negative 11, 3, 0. And I get 1 times negative 11, which is negative 11, plus 5 times 3, which is 15, plus 2 times 0, which is 0. And then my last row times my column vector, negative 3 times negative 11 is 33. Negative 7 times 3 is negative 21, plus 6 times 0. And my final answer is going to be -2, 4, 0, which is exactly what we had hoped to get. Sorry, -2, 4, 12. -33 minus 21 is 12, and then plus 0. So -2, 4, 12. That is the B that we were given. Okay, is B in the span of 1, 1, -3, 3, 5, -7, and -4, 2, 6? Those are the three vectors I was given. We just showed that B, -2, 4, 12, is a linear combination, and the weights that we would put on these vectors are -11, 3, and 0. And is B a linear combination? Yes. Okay, so now A is the same vector, 1, 1, -3, 3, 5, -7, and -4, 2, 6. And instead of using a specific B, like we did earlier, -2, 4, 12, I'm going to use a generic B from R3, B1, B2, B3. So to write out the matrix equation, AX equals B, I'm going to have 1, 1, -3, 3, 5, -7, and -4, 2, 6, times my vector of unknown weights, x1, x2, x3, equals my generic vector B. Instead of this specific one, I'm going to use B1, B2, B3. To translate this into a system of linear equations, this says x1 plus 3x2 minus 4x3 equals B1. x1 plus 5x2 plus 2x3 equals B2. And -3x1 minus 7x2 plus 6x3 equals B3. Okay, now we're supposed to row reduce the matrix A. This is the coefficient matrix of the system, not the augmented matrix. So matrix A is 1, 1, -3, 3, 5, -7, and -4, 2, 6. So I've already done most of the work for this problem when I row reduced when I was solving with a specific B. So I'm just going to copy it from earlier. And this row reduces to 1, 0, 0, 3, 1, 0, -4, 3, -12, -2, 3, 0. Now this is not completely row reduced. It's not in reduced row echelon form, but it is in echelon form. I have my pivots along the diagonal, zeros below them all. So the question is, does our result from 4C have a pivot in every row? Yes. Pivot in row 1, pivot in row 2, pivot in row 3. So does the matrix equation AX equals B have a solution regardless of the choice of B? Right, because this was for a specific B, so I'm going to erase that. This is the row reduced matrix A. So if I had augmented with a B, I would still have 1, 0, 0, 3, 1, 0, -4, 3, -12, and then I'd have like some stuff that has B1, B2, and B3 in it, and some stuff. Right, so this will always have a solution, because the only way I wouldn't have a solution is if this were a 0 and this were not a 0. But because of this -12 here, I'll never end up with something that's untrue. So yes, this will have a solution regardless of the choice of B. And that is the definition of the columns of A spanning R3. Yes, so if you can find weights to put on the columns of A so that you can build any vector in R3, then the columns of A span R3. So how do the results from this question make answering 2F and 2G easier? Or 2E and 2F probably? The pivot. You just want to look at the pivot in every row. That tells you whether the columns span the entire space and if there's a solution regardless of the choice of B. To show that the equation AX equals B does not have a solution for all possible B, I'm going to row reduce the coefficient matrix A. So I have 2, -6, -1, 3. I'm going to scale the first row by a half so that I get 1, -1/2, -6, 3. And then I'm going to knock out this -6 by doing row 2 plus 6 row 1. So row 1 is not going to change. And row 2 becomes 0. 6 times -1/2 is -3. -3 plus 3 is 0. So because in the coefficient matrix I have 0, if I were to augment, I would end up with 1, -1/2, 0, 0, and then I would have some stuff over here. Some stuff that, some combination of B1s and B2s, stuff involving B1s and B2s. So it's possible that this third row could end up as 0 equals a number, a non-zero number. Okay, so the fact that there is no pivot in row 2, row 1 has a pivot, but row 2 does not, that tells me that it does not have a solution for all possible B. There's got to be some B in there that will make 0 equal a number. Okay, so I want to describe in set builder notation the set of all B for which AX equals B does have a solution. Okay, so I have to be a little bit more careful to answer this question. Up in part A, I row reduced just the coefficient matrix. I'm going to do a similar process, but I'm going to augment with B1, B2, because I need to figure out when this stuff is 0. That is when I when I do have solutions. Okay, so I have 2, -1, -6, 3. I'm going to augment that with B1, B2. And then I'm just going to do one step to knock out the -6 below the 2, below this first pivot. I'm not going to scale first. I'm just going to knock out the -6. So I'm going to do row 2 becomes row 2 plus 3 row 1. And that's going to give me 2, -1, B1. Row 1 doesn't change. And then row 2 is going to become 0, 0. And then row 2 plus 3 row 1 is B2 plus 3B1. And this system will be inconsistent if this number is not 0. So no solution if B2 plus 3B1 is non-zero. So any B1 and B2 that satisfy that equation will give me an inconsistent system. So that means that it does have a solution. This system does have a solution if B2 equals -3B1. This is how we'll have a solution. If this number is 0, there's no inconsistency in the last row. So we have a solution if B2 equals -3B1. So to write that in set builder notation, I'm going to come down here and finish this. So in set builder notation, any vector that satisfies this equation I will have a solution. So it's going to be B2 is negative 3B1. So I'm going to have B1 and B2, the second entry is negative 3B1, such that B1 is any element of the real numbers. Describe the set from part B using the word span. So this set using the word span, I would take the span, which means the set of all linear combinations of 1, negative 3. Because B1 is just being multiplied by both entries. Do the columns of A span R2? No, because there are vectors for which we have no solution.